All right, now let's go through a few examples. So the first problem we have, we're given 6 vectors. Each of these vectors have four components. So these are all vectors in R4. And we are asked to find the largest possible number of independent vectors. By the way, if that number is 4, then we would really be finding the dimension of R4. Since these vectors are vectors in R4, we know that there cannot be more than 4 vectors which are linearly independent. We don't have to, so we are looking for the largest possible number, so we don't have to, it doesn't matter which vectors we pick. The point is to decide whether we have 1, 2, 3, or 4. So let's start looking at the vectors. So if I look at the first vector and the second, I see that the second vector is not a multiple of the first, so these two are definitely linearly independent. Furthermore, if I combine them, observe the first vector has a 0 in the last position, and the second vector also has a 0 in the last position. So if I combine these two vectors, I cannot get something non-zero in the last position. Now this tells me that V3 cannot be combined with V1 and V2 to give 0 in a non-trivial way, unless I multiply everything by 0. Or I cannot express V3 as a combination of V1 and V2 because V3 has -1 in the last position. So I see that these 3 vectors are definitely linearly independent. Now what about the fourth vector? Could I express the fourth vector as a combination, V4, as a combination of V1 and V2? I'm not going to use V3 because V3 has non-zero here, whereas V1 and V2 have zeros, but also V4 has a 0. So the question is it true that V1 and V2 span V4? Or in other words, is it true that V4 is a linear combination of V1 and V2? And how can we see this? Well, if I'm trying to combine these vectors, maybe it's time to write. So let me look at the vectors V1, V2, and V4, and I will try to combine them so as to get 0. So I might multiply them by something. I'm reserving some space here. Since everything is 1 and -1, I'm likely to multiply them by a 1 or -1 as well. Nothing more than that. And I want to combine these vectors to get 0. So the question is how to do it. Well, first of all, if you pay attention to the first row, the vector V4 has a 0, so it doesn't matter what I multiply by here, that's not going to change this 0. So then I have this vector and this vector, and they both have 1s in the first position. So in order to get a 0, I better have a 1 and a -1 for their coefficients. Question is which? Well, okay, I have 2 candidates. I either do 1 here and -1 there, or the other way around. But I need something like this. Now, what about the second row? Well, I now see in the second row that I have this -1 multiplied by a 1, and I have this 1 multiplied perhaps by a 1 there. So maybe I can add a 1 there. We'll see, maybe that works, maybe it doesn't. So far so good. The first component is taken care of, I'm getting a 0. The second component is taken care of, I'm getting a 0. But what about the third one? So the third component is here in the first vector, it's a 0, so it doesn't matter. I have negative 1 times negative 1, that's a 1. And then I have 1 times negative 1, which is negative 1. So the third component also is a 0. And the fourth component is a 0. So what do I see? I see that V4 is actually a linear combination of V1 and V2. So remember, these were, or this combination is V1 minus V2 plus V4 is 0. So in other words, V4 is V2 minus V1, right? So I cannot take V4 into consideration with V1, V2, and V3 because V4 is a combination of these three vectors, or rather V1 and V2. All right, now let's consider V5 with sort of a similar idea. No point in looking at V2. Why? Because V5 has a 0 in the first component, whereas V2, well, I'm wrong here. There might be a point in looking at it. So, can I express V5 as a combination of V1, V2, V3? That's the question. And then can I express V6 as a combination of V1, V2, and V3? So, of course, we could solve this system simultaneously by just setting up a system or by setting up a matrix. So we can play like this to try and understand, or we can just use what we know about matrices. So I'm going to start by making this big matrix that has V1 through V6 as its columns. So I know I'm going to have at least 3 pivot columns, but am I going to have more? And that is not obvious. Actually, now I see something that says, yes, it is obvious that I cannot have 4. Why is that? Well, if I add all the components of V1, I get a 0. If I add all the components of V2, I get a 0. If I add all the components of V3, I get a 0. Same is true for V4, V5, V6. So now, when I'm looking at this matrix over here, what I see is that if I add all the rows together, I'm going to get a row of zeros. So I will do exactly that. I won't try standard elimination. I will say row 1 plus row 2 plus row 3 into row 4. Plus row 4 into row 4. So I'm adding all of them together. Now, remember, this is a linear combination. So of all the 4 rows. So I'm just writing another linear combination into that new matrix. What I will get, 1, 1, 1, 0, 0, 0, negative 1, 0, 0, 1, 1, 0, 0, negative 1, 0, negative 1, 0, 1. And then you see I will get zeros everywhere. So I know that the matrix that I started with, let's call it A, cannot possibly have 4 pivots because its rows are dependent, right? I don't only have to look at dependent columns, I can also look at dependent or independent rows because the rows are also vectors. So I see that A cannot have 4 pivots because we just produced a row of zeros. In fact, elimination would do exactly the same thing. It would just take us more steps. So now we can see very clearly that the first 3 columns are linearly independent. How can we see this? A rearrangement would show us the case, but also, I mean, here you have even if you just focus on the 3 by 3 matrix, you see that that these two vectors are independent and that this one cannot be produced from the other two. So reason being, you have zeros in these two positions. You cannot combine these two vectors so that this -1 and that -1 cancel each other out in some way to produce zeros. That would be impossible. So the answer to this question is the largest possible number of independent vectors is 3. So even though we have 6 vectors, we see that v4, v5, v6 can be described by the vectors v1, v2, v3. Of course, we could also express v1, v2, v3 through the vectors v4, v5, v6. So the choice of how we arrange these vectors into the columns of A, remember the process of elimination will always push pivot vectors to the left. So if you took these 3 vectors as the first column vectors, then you would get pivots in different locations because these ones won't play much of a role. All right, so more than one way to address this problem. The most basic one, if you can't see any relationship, I just happened to see that all the rows of the vectors or all the components of the vectors add up to 0, and I knew right away that my rows in the matrix A would be linearly dependent. And then knowing that I have at least 3 pivots, finding that one relationship for the rows told me that I cannot possibly have 4 pivots. So I knew I had already found the maximum number. But as a strategy, you could always just start by making that matrix, carrying out elimination, and counting the pivots. You don't have to go to the reduced row echelon form. It is enough to go to an upper triangular form or a row echelon form of A. All right, now let's look at another example. This looks a little bit more theoretical, perhaps, although that doesn't make it harder. So we're given 3 vectors, w1, w2, w3, and we're told that these vectors are independent. So the only way to combine them to get 0 is if you just multiplied everything by 0. We are asked to show that these differences, v1, v2, v3, so that's w2 minus w3, that's a new vector. Then v2 consisting of w1 minus w3 and v3 consisting of w1 minus w3, that these 3 vectors are in fact dependent. How are we going to show this? Well, observe here, if I were to add these 2 vectors, what's going to happen? Do I want to add them? How can I show that they are dependent? And I feel that I've copied this question wrong. So this doesn't make sense because the way I've written it is that v3 and v2 are exactly the same. So what we have here is, in fact, this should be a w2. All right. So how can we show that these 3 vectors are dependent? We're looking for some combination of the 3 vectors that will be dependent. Now, what's one way of looking at this? If I know that the vector v1 equals w2 minus w3, how can I write that as a linear combination? So I have 3 vectors, w1, w2, w3. Let me write a matrix W that consists of those 3 column vectors. w1, w2, w3. I don't know how many components the w's have. That's not important. So now, if I'm writing V as a combination of the W's, then I can write V1 as WX in some sense. So I could write V1 as this matrix W, so the vectors are W1, W2, W3. And now how do I combine them? Well, I don't take W1, so there is a 0. I take W2, and then I subtract W3. Okay, so V1 can be expressed as this matrix multiplication. Now, what about V2? So, okay, I need to rearrange my board a little bit. Bear with me. All right. Now, the next vector is V2 equal to W1 minus W3. I want to write V2 again as a column matrix, or as a matrix multiplication. So I will have W1, W2, W3, and I need to combine them to produce V2, and the combination is, well, take W1, so that puts a 1 here. W2 doesn't show up, so I have a 0 there, and W3 does show up with a negative 1. Okay? And similarly, V3 is given by W2 minus W3. Well, then V3 is this vector represented by this matrix vector multiplication. So, okay, I'm making mistakes here. So I should have 2, 3, 1, 3, and 1, 2. My apologies, I mixed this up several times. So let's say 1, 2 here. Otherwise it doesn't make sense. I've just copied the problem wrong. So I have a 1 and a 2 here. Otherwise things are trivially dependent and there is nothing interesting to look at. So here I have 1 minus 1, 0. Now I can represent these three products, right? These three calculations as a single matrix calculation in the following way. I could take these V1, V2, V3 and place them into a single matrix. V1, V2, V3. I'll call that matrix, surprisingly, V. That matrix, now I will carry this out as, well, maybe I'll write it and then you'll see what's going on. W1, W2, W3 times the matrix 0, 1, negative 1, 1, 0, negative 1, 1, negative 1, 0. So let me call the first matrix W and the second matrix A, right? I don't know how many components W1, W2, W3 have, but that's not important. I know because there are 3 columns that I can carry out this multiplication. Well, the rows of these A's, of the matrix A, add up to 0. So I know that elimination will produce a row of zeros. In this matrix is sort of similar to the previous example. So I know that the matrix A is not invertible, right? A is singular. If you can't see it, just carry out a couple of steps of elimination. Of course, you're going to have to exchange the first 2 rows to bring a pivot into that 1, 1 position, but eventually the third row will be a row of zeros. So A has only 2 pivot columns. What does that mean? So how can what is the goal I'm trying to reach here? I'm trying to show that the vectors v1, v2, v3 are linearly dependent. Well, that is the same as saying, so maybe I'll write the goal here. It's to show that the matrix V does not have full column rank, or rather that the null space of V is not zero, that there is something in the null space of V. So how can I show this? I think I'm going to need a bit more space here. So I have V is W times this matrix A, where A is singular, right? A is a 3 by 3 matrix. Let's see, 0, 1, negative 1, 1, 0, negative 1, and 1, negative 1, 0. Okay. So I know that that the columns of W are linearly independent, but the columns of A are not. So how can I show that V, the null space of V, is not zero? Well, simple. Find something in the null space of V, or rather show that it is possible for us to find an X that gives us V times X is 0, with X not being equal to 0. If we can find such an X, that X would be in the null space of V, which would mean that the null space of V is not simply the zero space. So how to show this? Well, let me rewrite V as W times A. Right? Vx0 is the same as saying Wx. WA times X is 0. But you see, I can find an X that gives me A times X equals 0. What is that X? So how can I find an X in the null space? How could we combine? Well, you see, if we take, just by observation, the coefficients of the second and third column, they have to be 1 and a negative 1, right? Because I need this one and this one to sort of cancel out when I add them up. So maybe I multiply this one by a 1, that one by a negative 1, or the other way around. And then it turns out that the first column and the third column have to have the same coefficients, because I want to be able to add 1 and negative 1. And then the first and the second have to have opposite signs. So the vector 1, negative 1, 1 should do the trick. Let's try. So take X equal to 1, 0, negative 1. Of course, you could do elimination and then find a linear combination of the columns that will be in the null space. We've done this, or in other words, find the null space of A, or find a basis for the null space of A. Oh, sorry, I wrote that wrong. This should be 1, negative 1, 1. Okay, let's see that works. So if I take the dot product, or I'm adding the first and the third row minus the second. So for the first components, I would have 1 times 0, which is 1. I would have negative 1 plus 1, that gives me 0. Here I have 1 and negative 1, that gives me 0. Here I will have negative 1 plus 1, that gives me 0. So this definitely is in the null space of A. So then A times X is 0. And from here, W times AX is also 0. Why? Because this is 0, right? We know that there is no way to combine the columns of W to get 0, but A times X is 0. So Since W times A times X is 0 and X is not 0, this is the same as saying V times X is 0. So X is in the null space of V, which means that the null space of V is not 0. So this is how we can demonstrate that V1, V2, and V3 are linearly dependent, even though we don't know how many components they have. Because you see here, this is a bit of use of theory, so maybe it's not the most straightforward example, but that's kind of the idea of why I'm showing it to you. We cannot use direct elimination on the columns of W, or on the matrix, on the matrix V, not W. So I said if you have three vectors, how can you tell whether they're independent or dependent? Well, stick them into a matrix and carry out elimination. But we don't know what these vectors are. And yet, we're able to show that they must be linearly dependent through this matrix A. Yeah, this seems like a lovely test question or something similar like this to go on a test. All right. Next problem. We have two matrices, A and U, and we are asked to find the dimension of four spaces. So what are these spaces? I want the dimension of the column space of A. In other words, what is the rank of A? In other words, how many pivots does A have? This answers the first question. Now we want the dimension of the column space of U. So how many pivots does U have? This is a very simple question. I mean, we already know the answer because U is in a reduced form. So we know that the dimension of the column space right away is 2 because these are the two pivots. Whereas in A, we don't see the pivots right away. So we have to think a little bit about this. Now, what about this C of A of T? So the column space of the transpose of A. This is also referred to as the row space because you see, if I were to transpose the matrix A, its rows become columns of A transpose. So the column space of the transpose really describes the row space of the matrix A. So this is row space of A. And similarly, this is the row space of U. Okay, now, finally, the next question will be which two of these spaces are the same? And that's an interesting question, and it hints to something that we are going to fully describe in the next lecture. But we still are capable of sort of investigating at this stage. So we have an answer for B right away because U has two pivots. So what can we say about A? Well, I can sort of do it by observation, but we could also just carry out elimination on A. So I'm going to choose the second way. I'll carry out elimination on A. Here's my A, 1, 1, 3, 1, 3, 1, 0, 1, negative 1. And I'll start eliminating. The operations would be R2 minus R1 into R2, R3 minus 3R1 into R3. What am I getting? I have 1, 1, 0, 0, 2, 1, 0, then 1 minus 3 is a negative 2, and a negative 1. I see that the second and the third row are essentially the same, or they're multiples of each other. So if I just add them up, row 1 plus row 2, row 3 plus row 2 into row 3, what I will get is 1, 1, 0, 0, 2, 1, 0, 0, 0. So the way that the problem was stated was not exactly obvious that U is in fact the row echelon form of A. But now that we carried out this elimination, we know for a fact that to be the case. So certain things can be answered immediately. The dimension of the column space has to do with the number of pivots or the number of pivot columns of A? Well, we know that the number of pivot columns in A is the same as the number of pivot columns in U. And the same is true for the rows. The number of pivot rows in A is the same as the number of pivot rows in U. So the answers to these questions under A, the dimension of the column space of A is 2. For B, the dimension of the column space of U is also 2. For C, the dimension of the row space, now remember, this asks how many linearly independent rows there are in A, and the answer is again 2. So the rank gives you sort of the same information. Tomorrow we'll make that formal, but really for any matrix A, the dimension of the column space is the same as the dimension of the row space, because the pivots don't really care whether they're in rows or in columns. A pivot cannot be in, or one row cannot have more than one pivot, one column cannot have more than one pivot. Therefore, the number of pivot columns is the same as the number of pivot rows. Therefore, the dimensions of the column space and row space of a particular matrix are the same. So for D, we also have that the dimension of the column space of U transpose, which is the row space of U, is also 2. So this was easy. The more interesting question is which two of these spaces are the same? Well, the row space and the column space are definitely, well, are they definitely not the same? We cannot say for sure, but clearly between, okay, let's start from the beginning. Let's look at the columns of A. Whoops, I should not have done that. The columns of A and the columns of U. Could the column space of A be equal to the column space of U? The answer is no. Why is the answer no? So remember, pivot columns of a matrix give us a basis for that space. Now, the pivot columns of A correspond to the pivot columns of U in the sense that if the first two columns of U have pivots, then the first two columns of A are independent, they are pivot columns, whereas the other one will be a free column. So when you look at the columns of A, they have a non-zero third component, whereas the columns of U do not. So no matter how you combine the columns of U, you're never going to get a non-zero third component. So for sure, the column space of A is not the same as the column space of U. Unless A and U are the same, you cannot make such a statement. So then, what about the column space of A transpose, or rather the row space of A and the row space of U? So if I look at the rows of A and if I look at the rows of U, can I say that these two spaces are the same? The answer is yes. The row space of A and the row space of U are the same. Why is that the case? So, how can you show that two spaces are equal, right? Well, we need to show that when we choose a basis for A, for the row space of A, and when we choose a basis for the row space of U, that their linear combinations actually describe the same space. Okay, so let's take a basis for the row space of A. So what would that basis be? Well, it would be the pivot rows. So it would be the first two rows of A. 1, 1, 0, and 1, 3, 1. Right? Those are the pivot rows of the matrix A. And then if we want a basis for the row space of U, those would be the first two rows of U. So they would be 1, 1, 0 and 0, 2, 1. So not the same vectors, right? These are different vectors, or rather, the vector 1, 1, 0 is in both of these bases. So that's okay, that's good news. But the row space of A has this other vector in the basis, 1, 3, 1, whereas the row space of U has the vector 0, 2, 1 in this basis that we've chosen. So the question is, can we combine the rows, can we combine these two vectors to obtain that vector? And the answer is absolutely. How do we know? Well, how did we get the row 0, 2, 1? We combined the first two rows of A to obtain 0, 2, 1. We took the second row minus the first, and we obtained 0, 2, 1. So definitely, the vector 0, 2, 1 is in the span of these two vectors. So we know that this is in the vector space here. We know that this vector is in the row space of A transpose. Now, to show equality, I also have to say, well, is it true that the vector 1, 3, 1 is a linear combination of these two vectors? In other words, could I go back? Well, we have seen that it is definitely possible to reverse these operations. How do we go back? We go from a minus into a plus. Namely, if I add these two rows, I'm going to get that row. So we see that I could express this vector as a combination of these two, and I can express this vector as a combination of these two, which means that the spaces spanned by either of these bases, they are the same. So that's how we test whether two spaces are the same. Now, there is one other question to ask. Is it true that the row space of U, for example, is the same as the column space of U? The answer would be absolutely not. Why is that? Well, the rows do have a non-zero third component, so I could make many vectors with a non-zero third component, but there is no way to combine the columns to get a non-zero third component. So definitely the row space and the column space are not the same. They both describe a plane in R2, but not the same plane. So for U, we know that the row space and the column space are not the same. Maybe I should write that somewhere. So the column space of U is not the same as the column space of U transpose. It is possible for the row space and the column space to be the same. And what about the row space and the column space of A? So this is something that we have to investigate in some sense. This is not a trivial answer to give. They will both describe planes, but will they be the same? How can you answer this question? Is it true that the column space of A is equal to the column space of A transpose, or the row space? In general, these two spaces are not the same. So we're going to have to take a basis for the column space of A, and that basis could be the first two columns, or the first and the last, or the second and the third column. So any two columns of A give us a basis for the column space of A, and any two rows of A give us a basis for the row space of A. So we would have to look at a similar argument where you take something from, when you take one vector from the row space and you try to show that it is in the column space and vice versa. In other words, another way to show this would be to take the first two rows of A and the first two columns of A, stick them into a single matrix, and check whether or not you have only two pivots. If only the first two columns are pivot columns, that will show you that the other two columns are combinations of the first two, and you would say, yes, these spaces are the same. But if you get a pivot not only in the first two columns, but maybe first in the third, actually in this case you would either have 2 pivots or 3 pivots. I have a feeling you would get 3 pivots in this particular case, and that will show you that there is something in the column space or in the row space that's not in the column space. So if you wanted to check this particular question, so this is in general not true. If you want to answer it for this particular matrix, take the first 2 rows of A, put them as columns of a matrix, and then the first 2 columns of A, put them as 2 additional columns in that matrix. Carry out elimination. If only the first 2 columns have pivots, then your answer is yes, the column space and row space are the same. But if you get 3 pivots, then the answer is no, the column space and row space are not the same. All right, one more problem, and that is enough for today. And I'm hoping that these examples are helpful and not more confusing. All right, find a basis for each of these vector spaces of R4. So under A, we want all vectors whose components are equal. Well, I can think of many different vectors here, but really there is kind of a generic way. So we have one condition. We want their components to be equal. All components need to be equal. So what's a typical vector where you have all components equal? Well, that would be the vector 1, 1, 1, 1. But you could also do it like this. So if I take a typical vector with all components equal, then that vector will look something like this. A, 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 A. So this vector is a multiple of the vector 1, 1, 1, 1. So you see, I can express any vector in this space, so the space that has all vectors whose components are equal, as a linear combination or a multiple of the vector 1, 1, 1, 1. So the basis in this case, or a basis, would be simply the vector 1, 1, 1, 1. Of course, I could take the vector 2, 2, 2, 2, or the vector negative 3, negative 3, negative 3, negative 3. They would all be multiples of exactly one vector. So this space has dimension 1. Now, part B, it says all vectors have to have components that add to 0. So what are such vectors that I could have? Well, I could have, and we saw examples of this in the first and second problem. So I could have A, negative A, and then the other two could be zeros. This would do the trick. And this is now A times the vector 1, negative 1, 0, 0. Or I could have the first one to be A, the second 0, the next negative A, and then 0. So this gives me the vector A times 1, 0, negative 1, 0. And the third way to get 0 would be if I put A here and then negative A there. Now you could say, what about other places? So what are these 3 vectors? 1, negative 1, 0, 0, 1, 0, negative 1, 0, 1, 0, 0, negative 1. Let's go back to the first problem. Those are exactly these 3 vectors, right? This, and this. If you look at these 6 vectors, these are all the ways in which you can build a vector with 2 components equal to 0 and 2 components not equal to 0 that add up to 0. We saw that at most 3 of them are independent and the other 3 have to be linear combinations of these 3 vectors. So in fact, these 3 vectors give us a basis. These 3 vectors also give us a basis. Any 3 which are linearly independent give us a basis, and in fact, in this case, any 3 vectors are linearly independent, but no more. So when you have one condition that normally reduces that freedom, you cannot have vectors, you cannot have the entire 3 space. So a basis in this case would be these 3 vectors: 1, negative 1, 0, 0, 1, 0, negative 1, 0, and 1, 0, 0, negative 1. If you want to combine the vectors in any other way, any other vector, any vector that will have the sum of its components equal to 0 will look like this. Will be a combination of these 3 vectors. All right. Question C is actually very, very interesting. It's trying to hint as to what is to follow. We're looking for vectors, all vectors that are perpendicular to 2 given vectors. So these are vectors in R4, it's just they're written horizontally to save a little bit of space. So what am I looking for? I'm looking for vectors in R4 such that when I take the dot product with this vector, I get a 0, and when I take the dot product with this vector, I get a 0. Well, the easiest way to do that would be to stick these 2 vectors into a matrix as the rows of that matrix. So let the matrix A be equal to 1, 1, 0, 0, and then 1, 0, 1, 1. Then the null space of A will have all vectors that are perpendicular to the rows of A. Why is that the case? Well, what is the null space? The null space of A consists of vectors x such that A times x is 0. Well, when you carry out multiplication A times x, how do you compute it? Well, you take the first row, you multiply it by x, and you want to get a 0. Then you take the second row, you multiply it by x, you want to get a 0. So you see this vector x is orthogonal to the rows of A. So to find a basis for the space of all vectors which are perpendicular to these 2 vectors given here, all I need to do is find a basis for the null space of A. So let's find a basis for the null space of A. Okay, I will copy that matrix A here. 1, 1, 0, 0, 1, 0, 1, 1. So let's find a basis for the null space of A. To do that, I could play with the columns as they are, or I could carry out elimination. I'm going to carry out elimination just because that makes things a little bit easier and gives us a systematic approach. So I have R2 minus R1 into R2. And in fact, I'm going to get to the reduced row echelon form. So I have 1, 1, 0, 0. Then I have 0, negative 1, 1, 1. And that one more step which eliminates above the pivot, and then I'm going to multiply by negative 1. So I have R1 plus R2 into R1 to give me 1, 0, 1, 1. Then I have 0, negative 1, 1, 1. And then the next elimination step, which is not really elimination, I want the second pivot to be positive, so I know that the result will simply be a plus here and then minus, minus. So that would be my reduced row echelon form of A. Right, that's the matrix R. And just so these pluses and minuses don't confuse us, I'm going to rewrite them. So you first do this operation, and after that, minus R2 will go into R2, and we're going to get a 1, a -1, and a -1. So now I see that I have my two pivots, right, as was to be expected. And now the null space of R equals the null space of A, we know that. So the null space of R is the same as the null space of A. There are two free columns in R, and each free column gives us one vector which will go into the basis for R that we are trying to find. So what are such vectors? I'm trying to, so if you remember, we would set, so think of the columns as coefficients, or as columns for x1, x2, x3, x4. So x3 and x4 are the free variables. I'm going to set x3 to equal 1 and x4 to equal 0. That will give me a special solution. So what is that special solution? From the second equation, x4 is 0, so x3 is -1, then it will give us -1 because it's -1 times 1, then that forces x2 to equal 1. So I will have a vector x, which has 0 for x4 and a 1 for x3. From the second equation here, that forces x2 to equal 1. So you can try multiplying, but we still need, it doesn't matter. The interesting thing is it doesn't matter what this component is. If you take the dot product of this vector with this row, because it's multiplied by 0, it won't matter, and indeed you have 1 minus 1 is 0. So we know that this vector is orthogonal to the second row. We just have to make sure it is orthogonal to the first row. This 1 is multiplied by a 0, so it doesn't matter. So since this 1 hits this 1, we have 1 times 1, then this better be 1 times a -1. So I know I have to have -1 here. If you can't play with the numbers the way I am, just take your time, write the equations, and you will find the vector, the first vector x, or maybe I should write special solution S1, because these are the special solutions. And then for the second special solution, we're going to set x3 to 0, whereas x4 will now equal 1. So the second special solution will have 1, 0 here. From this equation, because these are both -1s, I know that this coefficient will ask for a 1 right here. So you can try taking the dot product of S2 with the second row of R. You are going to get 0. Now let's look for the first coefficient, and for that we have to look at the first row. So we have 1 times 1 here. So this one and this one multiplied to give a 1. This 0 means don't worry about x3. That 0 means don't worry about x2. So then I better have a -1 right here. Now you can just check that this is truly the case. Just take the dot product of S2 with the two rows of R. But also what you could do is take the dot product of S1 and S2 with the rows of A. So let's quickly do that. So the first row of A has a 1 and a -1 in the first two positions, whereas S1 has -1 and 1. So when you take the dot product, you get 0. And S2 has those first two coefficients equal. So the first row of A dotted with S2 also gives a 0. And then when you do that with the second row, we have 1 times -1, which is -1, plus 0, that's not interesting, plus 1. So far, if we're keeping track, that's 0, and then you have 0 times 1, which is 0. And similarly, the dot product of this row with this column gives us 0. So the basis in question is these two special solutions. As I said, a basis is not unique, but this is our systematic approach to finding a basis for the null space. So we'll have uniqueness for as long as we stick with looking for these special solutions. All right, and that was part C. Now, what about part D? We're looking for a basis for the column space of the identity matrix. Well, the identity matrix is an invertible matrix. Therefore, all of its columns are linearly independent. Now remember, we can always take the columns of a matrix to look for a basis for the column space. And since for every invertible matrix, the columns are linearly independent, we know that the basis is just the columns, consists of just the columns of the identity matrix. Or a basis consists of the columns of the identity matrix, and the null space of the identity matrix is just 0. We don't really treat the 0 vector as a basis, because the 0 vector is sort of escapes the definition of a linear independence, although you kind of only have one vector, but we essentially say that there is no basis for the 0 space. We will just say that the null space of the identity matrix is 0. So I do have enough space to write the answer for D. I don't want to change boards just so we can look at this. So the basis for the column space of the identity matrix would be just the columns of the identity matrix. And we will say that the null space of the identity matrix is 0. We will not say that 0 is a basis for the null space of A, because 0 is never a part of a basis. So in this case, you could say that the null space of I doesn't have a basis because it is the 0 space. And with that, we are done for today.